So to show you the solution of this one sample variance ratio test in R then, so one thing to sort of say here is that this is a slightly non-standard test, which for this example means it's slightly fiddly to do this in R. Other examples will be easier. So the first thing you have to do is calculate a number in the sample. So here this is done by this set of commands here. So the length just gives you the number of observations in the variable difference, sample size in this case. Then you need to calculate the k-square statistic. So this is the first principles. This is how we would do this in R, and in this case sigma squared equals to 1. Calculate the p-value like this, and you get in this case that the p-value is very low, computationally 0 according to R, and in this case in terms of the interpretation, so with significant evidence p equals 0.000 less than 0.05, that the variance is not equal to 1. One thing to look for here is it doesn't matter if you do the thing by hand or using R, you should get the same numerical answer and the same interpretation in either case. Okay, this is one of the few examples where, because this is a non-standard test, the computation is actually easier in eViews than in R. The other examples in R, which be more standard, will work more easily. So if you've got access to eViews then, so in order to calculate this one sample variance ratio test, so the first thing you should do is open this file, one sample variance ratio work file, that's available on the module canvas page, and then once you've opened that file, what you have to do is double click on the variable in order to bring up the spreadsheet mode in order for the thing to work. And then to perform a one sample variance ratio test, it's a bit simple to the set of menu commands that you've done before. You need to do view and test, simple practice tests, denoted test value, right, variance is 1, click OK, and you should get an shown at the bottom of the slide. So exactly the same as before, it just looks superficially different because of the way that different software packages present results differently. Okay, now as we said before, if the thing isn't working, you do need it in spreadsheet mode. Okay, so if you're not working and you wondered what's going wrong, okay, you need to be in spreadsheet mode, which here means you just need to make sure that you've double clicked on this variable difference in order to bring up the spreadsheet. Okay, examples I said before where eViews is actually. The second test I wanted to talk about here is this two sample t-test. So this is going back to answering questions about a generic data set and about where the location is, where do you think a typical observation lives. So as part of that, you want to compare the mean of two independent samples, and you want to see if the mean of the two samples is the same or different. Got an example with some data on the next slide just to sort of make this extra clear. So in this case, what you do is form this t-statistic and test in exactly the same way as before. So what we've got in this t-statistic, so you've got on the top line the difference between the two sample means. On the bottom line, the first line refers to a pooled estimate of the standard deviation, and the second square root sign refers to a pooled estimate of the sample size. Okay, so the idea is that this thing can still work even if you've got two samples of different size. So in terms of the notation then, sample, n2 is the number in the second sample, x1 bar is the mean of the first sample, x2 bar the mean of the second sample, S1 squared is the variance of the first sample, S2 squared is the variance of the second sample. So to give an illustrative example then with some data, so suppose you've got wage data on 10 advertising professionals and 13 accountants, and you want to see if there is any evidence for differences in the average levels of pay. Okay, so the idea is that you could then use this two sample t-test to see if there is any evidence of a difference. So the numbers that you get from this sample of 23 individuals, 10 advertising professionals. Is that a meaningful difference that you see, or is it just something that could happen quite easily by random chance? And if you look on the set of equations that are involved on the previous slide, you should see that what is going to be involved is sort of operationalization of various things that you've seen before. So we're going to need calculations of two sets of sample means and two sets of sample variances. Okay, and this is a slightly more complicated formula involved here as shown on the previous slide, so it's going to be even more important that you take extra time and extra care when plugging in the numbers into the formula. Okay, so lots of repetition for what we've seen before, and it's good practice because the regression techniques that we'll correlate in the course will be similar to these basic tests. So as promised then, so calculating these statistics for the two-sample t-test does involve operationalizing lots of the calculations we've seen before. So I think it'd be worthwhile here just making a note that the number in the first sample is 10, and then the mean as we've calculated before, so all that you do is add up the observations, and then for the variance, this is the practical calculation formula that you need to use. You should have a n-1 here on the bottom. This is the unbiased estimator. Not all textbooks have this correct. And then the sum of xi squared is just literally summing squared observations, and then you would calculate the variance, putting the numbers in one by one like this. So it comes out as 90.2. And I would say here that the name of the game is always communication. So if you were preparing for a written exam where you had to do calculations like this, it is worth here writing down that the number n1, the number in the first sample, equals 10, and then make it obvious that you have calculated the mean and the variance for this first sample. So the difficulty here is just if you're doing this calculation by hand, want to be as systematic as possible. And then for the second sample, so again, get used to the idea the name of the game isn't just calculation, it is about communication information. So write very straightforwardly that n2 is just the number in the sample, which in this case is 13. The mean, as before, all that you do is add all the observations up and divide by the number in the sample. Gives you this number here, 51.6154 in this case. Now the variance, so again this is the formula to use in the practical calculation formula. You've got an n-1 on the bottom to reflect this is the unbiased estimate variance. Again, not all books will use the right formula here. Now this sum of xi squared is again just each observation and add them all up. And then if you plug the numbers into the variance formula one by one, you should get here that the variance is equal to 95.7547. Now in this example, I guess one of the things you should look for really is that you get answers for the mean and the variance that are of a similar order of magnitude for both samples. Okay, you would expect, because the data is something that's natural to compare, that you get roughly similar answers for the mean and the variance in both cases, even if there are slight differences. Calculate the t-statistic then. So what we've got then is that the top line is just the difference in the two sample means. The first term, the pooled estimate of the standard deviation, and I think the second term in the square root sign is a pooled estimate of the overall sample size in one by one. Now again, what I should say for this sort of second line here is note that on the top line the two sample means are roughly of the same order of magnitude, and if you look in the first square root term, the two variances are again roughly the same order of magnitude. So it is just possible that if these numbers are wildly different, and I suppose again it's noteworthy here that you've got approximately equal numbers in each sample, at least they're of the same order of magnitude, 10 and a 13 here. Do the calculation and the answer comes out as 0.464. Okay, so acutely aware that algebra is not a spectator sport, but the thing I wanted to sort of emphasize here is that you've got quite detailed and I would ask you to take your time and take care with this when substituting numbers in to formula on any exam. Doing this by hand then, so the next stage would be to reference the t-tables, so the number of degrees of freedom sample, the second sample 2, which should give you 21 in this case. The value that you need is the t21 value for 0.025. The t statistic is less than the value in the table, which is 2.08, therefore p. Then the thing to watch out for repeatedly with this is that the two inequality signs for this step should point in a different way if you're doing this correctly. So the p-value is less than 2.08, the p-value is bigger than 0.05, and then the interpretation, which is another important part of this course, and with a view towards dissertations and actually implementing these things ultimately. So there is no evidence p bigger than 0.05 for differences in the average pay amongst advertising professionals and accountants. So the average pay levels seem to be roughly the same for both professions. So the sense here, which there is a cross-check that you get in a sensible, real-world, common-sense interpretation here, the similar professions which seem to offer similar levels of average pay. Sample t-test in R. So because this is a relatively standard statistical test, it should be relatively easy to do. So what you have to do is first of all read in the data, then the basic command is t.test. Now because the t-test is such a commonly applied test, this is nicely optimized and operationalized in R and the R syntax. So the first set of commands here is needed to read in the data, and then the basic command you need is t.test. Now think of this as something that acts on the list, where the first name in the list advertises as the first sample that you're comparing, and the second name in the list, the accountant, is the second set of data that you're comparing. And note here also that it says advertisers in this t.test bit, and it's advertisers that is being linked to this set of data, and it says here accountants in the second part of the bracket, and it must match the set of data that is attributed to the word accountants in step 1. Okay, so the two names have to match in both step 1 and step 2, and in this case what you have once you get the results, p-value is 0.6467, bigger than 0.05, so no evidence of a difference, and you should get the same t-value as before. To do this in eViews, what you need is this 2-sample t-test work file that is available from the module Canvas page, and then you need this in spreadsheet mode again. So the way to do this is to highlight the two variables, advertising and accountants, and you would right-click this to do a 2-sample t-test. What you'd have to do is view test of equality, and then select test of equality, click OK, and then you get a whole set of results, but the first row of the table gives you t-test, and it gives you exactly what we had before but expressed slightly differently. So there is in this case. Okay, so all statistical software packages produce more information than you really need. You'll need a fraction of the ultimate capability and functionality. Especially true for eViews, so it's also true for R. And I also want to reflect here that you're getting the same value and interpretation in each case. You might get minor rounding errors when you do the thing by hand, but it doesn't matter which package you use, you should be getting the same answer and interpretation whether using R